这么多 coding。
Okay, so we'll get started with the lecture. Share the screen, share. Okay, so we're good. Okay, we have another couple of sessions. This one is kind of easy peasy, but the next yeah, it starts to get complicated here. This one, the end of this one, and then the following. I think the following is about the maps, and there it gets complicated. So yeah, I mean, if needed, we can take a little bit more time to go over this, because especially the maps is kind of important. And then by the end of the week, I'll try to give you individualized feedback on the projects, so that we don't drop that. So there is time, but just to do a bit of risk assessment to make sure that we stay on track. All right. Yeah, I'll open also later today quiz 7. As usual. So if you see that you're overwhelmed and you need more time, we can keep it open longer, so you can focus on the assignment 6. Okay. So
the quiz from last.
the quiz from this week is on last Monday's lecture, right?
It starts today.
I think so. Yeah. Yeah. So we're back on track. We started the quizzes. I think that's what we did at the beginning. We started them on Monday, and I let them open for 2 or 3 days, right? But if needed, again, we can delay that, so you can manage your time. Okay, so today we're going to focus on color. So usually, folks who start playing around with visualization, they start overdoing the color thing. You use it everywhere. You use it for encoding the data, and color is kind of one of the most tricky ones to get right, and you definitely don't want to overdo it. And in part of it is it's because there is a lot that is going on in terms of perception of colors. And if you start mixing colors and you're not aware of what bad things can happen, then especially when you have a lot of data and you want to use a lot of color, then definitely bad things happen. So you want to think also about the encoding. So this is a static picture. It appears to move, and it's your brain that is giving you those cues. If you fixate at some point, then things seems to stop, but they seems to restart somewhere else. So we'll see a few of these illusions. This one is you know, specially crafted, so it's really hard to get this thing to appear in graphics that are for displaying data. but we will see some illusions that usually can happen if you're not careful. So we'll start talking about how is it that we understand color with our heads and our eyes, and then talk a little bit about color theory and design. And the last two pieces are kind of the practice with D3. So what tools D3 gives you to work with colors, and what tools also D3 provides for doing complex charts. So we saw a couple of those already. I think we saw the area chart and the line chart, and we discussed it a little bit. So those are done with generators, but there are others like chord diagram and other more complex charts that D3 provides you already kind of a framework to put in place. So all you have to do basically is understand how to use it, and then you're able to create those. So we're going to see how to go scrape the code and understand it. And mostly here is just I have just a couple of slides. It's going to be mostly in the lab. All right, so we saw already when we discussed the visual system that what we perceive are basically wavelengths that are coming in through the eyes, and they're interpreted by the brain. And the wavelengths that we can see are parts of the visual spectrum. And for when it comes to color, we tend to associate a name with a particular wavelength. There is, as you can see, no such a thing as a pure color, unless you have a perfect source of color. So usually you have to deal with blends of colors. So we're going to try to understand that from the perspective of the visual system, how displays are created so that you can leverage the colors that you think you have in your graphic and that you want other people to see it pretty much in the same way. So your computer, for instance, is going to render color with some specification that are made so that everybody can see the same color. So we're going to see a little bit what tools people use for this. And we start with the light that is coming through our eyes and how we distinguish it. So there are three properties that you can associate with color. So U is what you usually associate with a color name. And it can be orange, yellow, green. So those are named colors. Again, that is only true for some of the pure colors, but most of this spectrum here is about mixed colors. The saturation has to do with the purity, because you mix color, if you want a red color that is fully pure, then you're going to get only the red wavelengths for the color. So usually that doesn't happen, and what you get is a mix of the red color and something else. Now you're going to say, oh, I don't understand this, because if I have a patch of red, then and I look at it, it's red. I'm only getting red. True and false. You're on the display. There is a pure red, but by the time it comes to your eyes, it's mixed with light that is coming from elsewhere. And so the red that you see is not exactly the same that is on the display, right? Just the background color, as we're going to see, it creates quite a bit of interference with the way we actually interpret a given color name. And so the saturation is kind of part of that problem. And the brightness is the last parameter. So sometimes you've seen these color scales that are HSV, hue, value, and saturation. So the value is the intensity, and when we talk about perception, we rather talk about brightness. But basically, you can think of it the same. So how much light is coming from the colored area to your eyes. So color vision is obviously, sorry. The scam is always coming at the bad time. So color vision obviously has to do with our ability to understand light that is of different wavelengths. And as we're going to see, this is about understanding how the brain really and the eye work together to create this this ability that we have to distinguish colors. But before we get there, we're going to look at the theories of color vision, meaning what ideas people have in terms of how this is actually working, because that has a number of implications in terms of how you use colors when you design graphics. So there are essentially two color theories that have been put out. As you see, that they're 76 years apart. The first one is the original one from Young and Elmos. So these guys are physicists, and they thought about the system as a physical system. And so they're very good with optics, obviously, and they understand the physics behind light. So they thought about how the eye forms the color and what is the brain doing with that information. And as you can see, it's trichromatic, and you're familiar with that, is the RGB. So the idea is that we have three sensors that are going to pick up the colors, and then it's somehow put together in the brain so that we can actually get to one particular color. As they did that, we're going to see that they did a few experiments where they tried to see how people, if you give them knobs and colored lights, if they can, how would they spin the knobs to replicate a given color. And that's important because if we all do the same, we use the same settings, it means that we're all able to understand the same color in the same way. Okay. Later on, there is this other theory that is the opponent process. So this one was formulated because people realized that the first one had some shortcomings. So we're going to see them in turn and look at the shortcomings so we understand why it's needed. So I don't know that this was known actually when Elmos and Young put together the theory that we have three different types of sensors. So those are the cones that we've discussed earlier that are mostly in the fovea. And now it's known that they respond to different wavelengths. So this is a normalized view of the response. We're going to see the actual response that is not normalized. You see it's normalized this one here. And the implication of that. So you see that all the blue, green, and red curves, they're all maxed out, but they are actually not all at the same intensity. So we have these three wavelengths, and that our eyes have sensors for. So based on the wavelengths, the people gave them names. So the small is the smallest wavelengths, around, you see, 400 nanometers. Then we have the medium and the large, spanning the blue, green, and red. So of these, with these 3 receptors, by mixing up the colors from those outputs, we can see about 10 million different colors. So what that tells you is that if you want a good screen or a good projection system for colors, you want to be able to somehow replicate what the visual system does, because then you're not cutting out on the number of colors that are usable, right? Yeah, so this is particular to humans, but other primates, they have the same type of system with these 3 receptors that are specialized. Some have 4, but yeah, most primates are seeing in the same way that we are. So as I mentioned, all the 3 receptors are cones, and they're mostly located in the fovea. That explains that if you look on, you don't want to look, but if you look straight and you think about what color you're seeing on the sides, then you'll see that it's quite difficult to tell the colors, and that's because you have very few cones on the periphery of the retina, and that makes for grayscale kind of vision on the sides. So you see things, but such as movement and objects, obviously, but the resolution is less because you have less of this both rods and cone. But you have very few cones that are away from the fovea, and that means that on the side you won't see color, either not at all or very poorly. So the association that we make between the S and L based on the wavelengths is shown here with the color. So usually we use this RGB nomenclature in order to refer to color, and we're going to see that that's what you do in most charting software. Now, what problem people have seen with this theory, where we say that everything is coming basically from these sensors, and then the brain mix it up as needed. So there are essentially 3. The first one is that there are some colors that culture don't usually associate a name with. So there is nothing between red and green, and nothing between yellow and blue. And that's peculiar because for the other colors, if you put them one next to the other, you can kind of smoothly move through it. But we have some trouble going through this reddish green because probably we have trouble seeing it. Because obviously there is such a thing. The wavelengths are continuous, and you should be able to interpolate in between those 2 colors. But it seems that the visual system has some trouble with that. The second problem is that if you look at the non-normalized response for the red, blue, green, blue, green, and red, that is small, medium, and large, you see that the blue we have many more or less. Like this is a logarithmic scale. If you look at it carefully. And then the other problem is that the green and the red here seem to be pretty much the same, right? So it doesn't really make sense that we're able to differentiate between red and green easily, because the responses, we basically have 2 responses that are very similar to one another, a little bit shifted, but still similar. Then if people look at the green and red, that is here M and L, if you just go and count them in eyes of people, you will see that the ratio varies a lot. But still, people are able to see colors in the same way, right? And so just having single sensors seem to say that either the brain is picking this up, which seems quite a bit of processing that needs to be done, or is doing something different. And the last one is the after images. So we're going to play in the lab with this. So after images are images that create when you stare at something without doing any saccade movements. So you're staring here, for instance, at the center of the red or the green cross. And then if you stare long enough and we remove the green and cross with the red background, and we show you a white background, then this is what you're going to see. And if you try to explain this with red, green, and blue sensors, it doesn't seem to make any sense, right? So for all these reasons, people have thought long and hard, and then they come up with this other theory that says, well, the red and the green seems to be very close, so probably what the brain is doing a difference. And is mixing up the red and the green that gives some yellow, and they compensate for the difference in blue. So I didn't say it, but the number of blue detectors is much smaller than the other red and green, and that's why the response is so low. So in order to compensate, what the brain is doing is making differences between the red and green and the blue and the yellow, and also black and white for what is called the achromatic channel. So achromatic means no color. Chromatic means that there is a color, okay? So if you try to think of it as a process, then you realize that, well, there is some truth into the second theory, but there is also some truth in the first theory. And basically, they happen at different levels. So the trichromatic, sure, we have this red, green, blue sensors in the eyes, and that's what is happening at the level of the retina, right? But then, as the nerve connection go to the brain, then the brain is starting working out all these differences. And so it's going to combine the red and the green, and we're going to see that in the picture all this is actually stuff. All these operations, right? You're just thinking about neural networks. That's the type of linear combination that you're doing between inputs and outputs. So these are just carried out by cells. So there is a cell that is going to respond to the red in a positive way and to the green in a negative way. And then you do the operation and you get a value, right? And the brain makes sense of this value when it sees these two colors. And the operation is here the dark minus medium, that is the red minus the green. And same thing with the yellow and blue. It's a little bit complicated because you need to get the blue in the first place, right? So you need to earn the information from the red and green, and then subtract the blue. And so the brain is wired to do this. And we're going to see that people have seen evidence of this in the fact that we have cells that are doing this operation. The achromatic channel is, if you add, we're going to see with the color models, if you add red, green, and blue, then you get a grayscale value, and that gives you your achromatic channel, right? So there, it's mainly about looking at brightness. So these two processes, the trichromatic and the opponent process, they work together. Again, it's important to understand that because from each one you have some lessons to keep in mind as you use the colors. Okay, so now when it comes to colors, I've made this long introduction to. This is weird because the projector seems to be skewed, but the effect is still there. So I made this introduction to say that you never have anything such as a pure color because there is interaction from all elements that are coming that are emanating light that is going to hit your eyes. So you never have a pure color that comes at your eyes. And so that's one aspect. The other aspect is that we have evolved to work in different lighting conditions. So early in the morning and during the midday and late during the day and even at night, we have drastically different lighting conditions. And so when it comes to interpreting colors, the brain uses all the information that comes from the sensors, but also tries to take into account lighting. So you will see the colors, and you know that differently depending on the time of the day, or depending on how objects are lighted. So in this particular example here, it's an illusion. So again, this takes quite a bit of time to put together, and is not something that normally happens in a graphic unless you do the risky stuff, that is to start using shading and 3D, right? And usually you want to stay away from those because, as we're going to see next week, they just create more complexity than they're useful. So in this particular one, you have the cylinder that is casting a shadow on the checkerboard. And so the question here is the color for the A square the same as for the B square? Is it or is not? Yeah, so the fact is that it is. And your brain is really tricking you into believing that it's not, because it's taking into account the lighting and makes a correction to the color, right? So this B square there, you're seeing it in the context of all the rest of the colors that are part in there. And when I say color, this is a checkerboard that is on a grayscale. So here we're looking at color as achromatic, but you get the same effects with chromatic. Right, so here we put just two bars on top of the squares that are exactly of the color of the squares, and you see that now we're kind of breaking the effect, but still, right? It's still difficult to tell that A is the same thing than B. You see it because the continuity of the colors, when you look close to the squares and to the bar, there is no difference. But because they're far enough apart and the one is shaded, the other is not, the brain is really changing the way you see these things, right? And what the brain is telling you is that, oh, these bars that are floating there, they're just floating. They're not part of the same object, right? So the brain is working hard to try to preserve the solution that it has come up with. So there are cases where this illusion come up that you need to know. So this is the one that is typical when you build a legend with keys. So the keys are the colors that you associate with the categories in your graphic and that you put in the legend, annotated. And you see that here the illusion is that these squares that are exactly of one color, they appear to have some type of gradient where the color gets darker on the left side, and this one gets lighter on the left side, right? So those are called MAC bands. So the way people avoid this is that you just separate with a space, because we're going to see what happens. But the result of your brain doing some good things ends up creating these artifacts that are not there. So if you want, in this particular case, I would say that, you know, if I use this color as a color scale to color my data, then you're telling people which color should I look at, the darker one or the lighter one in the graphic, right? And so just because you create the spread, you create uncertainty on the data. This is an example. If seizures are not your thing, they don't look at it too much. In this particular one, there are dots that appear. It's probably more apparent when you see it on the slides, but there are dots that appear here at the center, and it's basically the same effect a little bit from the MAC bands that happens at the corners. As the colors on the neighborhood are integrated and the brain is trying to do this kind of 2D MAC, the same thing that is doing with the MAC bands, but here in 2D. Yeah, so this doesn't happen, but it's just so that you understand a little bit how it works. The premise that we saw is that the brain is doing all this operation, and it does it with cells that integrate information from the sensor in the eyes, and they do this so similar how you would do it in a neural network with layers, right? So you have essentially two types of cells, both of which have been proven to be in existence. So the first one is the single opponent, so where you compare the red and the green. So this is the operation from the opponent channels. And then you have these global opponents that compare, you see here, an integrated version of this. And these, they usually have a larger support, meaning that that more neurons feed into these receptors, right? Which also means that you're looking at a larger field of view. So we're going to see that these are useful to understand colors over shading. So the lateral inhibition, this is this integration of say the single opponent cell, and this is the phenomena that is behind the MAC bands. So here, this one is on a white background. So the response here is going to remove more from the color here. And so this surface is going to appear darker than it is. And here, because here there is less light that comes at your eyes, there is less that is removed. And so this surface is going to appear lighter. Yeah? And that's exactly what is going on in your brain when the information is integrated in the MAC bands. Yeah. So yeah, I mean, these slides, I've put them in dark because this is information for you, but so that you know, you have a little bit of an idea of how it works, but I'm not going to ask you questions on that. The thing that is important to know is that is coming out of this is what is called the simultaneous contrast. And I put there universal because everybody is able to see these things pretty much in the same way. You see on the left side is in the chromatic channel, so we're using colors. The right side is the achromatic, where we just look at grayscale. And in both cases, the rectangles that are here are exactly of the same color, but you see that the background is making it that you perceive them as different colors, right? And it might, I think it's more apparent in the achromatic channel than in the chromatic channel. But still, you know, if you're doing this, then you know, if you have a color scale and these are your data points, you're going to make people's heads spin there, especially if your color scale is a continuous color scale, because they're not going to see the actual color that you want, right? So the lesson learned in terms of design here is don't use wacky backgrounds with colors, because colors can influence each other by this simultaneous contrast, and you want to minimize that as much as possible. That's why most of the charts that you see there, they have either a uniform background. Most of the time it's a white background, because then you're minimizing the interaction between the colors. Yeah, so again, simultaneous contrast, the colors of different objects affect each other. And that's really pretty much the take-home point from today when it comes to colors. So you remember the dual opponent cells that have a larger support? Those are the ones that are here helpful for understanding the colors across lighting conditions. So here, this part of the image here is in the shade, where this one is in direct sun. Still, you're very good at saying, oh, this is the blue, this is the blue, this is the green, this is the red here, right? So this is done with the double opponent cells that are able to look not just here, but at the same time look away from there. And the brain uses the shading information, as we saw in the first illusion. But this time it does it right, because it allows you to associate these areas. Yeah. And so this is called color constancy, right? Now, those are the universal, and I want to list here some of the individual that happen. So they're mostly related to vision deficiencies. So the first one is the one that I suffer when I look at fine text from too close, and that's the blurred vision. So you know, a lot of time you put a lot of textual information in your graphics, and or you use marks that are small. So in both cases, if people have blurred vision, then this is what is going to happen to them, right? And a lot of time you see this these charts with tiny axis labels that are not readable by most people. Obviously, if you're working in an area where, say, you're dealing with people of a certain age, then there are guidelines that you want to follow there. And we're going to see this in the lab. The second one that is directly related to color is the color blindness. So some people have trouble seeing certain wavelengths because either one of the receptor or several are not working correctly, or they're just not working. And then here the lighting is making things worse than they are. So this is somebody with a protonomaly. We're going to see what this is. But you see that it's very difficult for this person to read black text on a red background. So this is what a non-colorblind person would see. And here you see what somebody with protonomaly sees. So it's not as bad again, but the projector is not helping. Right, so you may think, oh, okay, I'm not cutting too many people out with this. Well, it turns out that about 10% of the population has some color blindness, mostly guys. As you can see here, maybe the males are the most affected. Some of them are very rare, like the tritanopia. So the nopia is that the detector is missing. The anomaly, so it doesn't respond well. But in both cases, you end up with more or less the same result. That is that the spectrum of colors that you see can change quite a bit. So the most of the cases are here, about 6% of the population, mostly males. If you don't care about males, that's fine. you can cut them out, but it's still 6%. And you see what happens is that they cannot differentiate between the red and green. And so that's usually what is referred to as red-green color blindness. The protanopia is the red sensor that is not functioning correctly. The teranopia is the green. But you see that obviously the effect is very similar between those two. So if you put them together, you're about at 9%, which is quite a big number. So as soon as you start doing putting data for a lot of people, if you're relying on the color to put out information because you're using a color encoding, and then you need to be extremely careful because you get 10% of the people, 1 in 10, that is not going to be able to read your data. Okay, second part here has to do with color theory. So as you use colors for building visualization, you want to somehow have a way of describing and manipulating colors. That is a kind of mathematical formulation. So color theory is really the practical concerns that are of color mixing that are in there. And the color model is what is referred to as the mathematical formulation of how you describe colors with numbers. And so you're already familiar with this. You know the RGB. There usually is an alpha that is added to that. There are other models that are used that we can take a look at. Starting with HTML and obviously SVG. So we know that the name of the attributes is different, but the way you specify the colors is pretty much the same between plain HTML and the SVG part. So what you do is that you have these tuples of red, green, blue, and opacity. You know that with JavaScript, if you omit arguments, then they are undefined. And so you can drop the opacity or drop the red and the green. And then depending on what the software does, it is going to attribute a view, some value to undefined that here I would guess goes to 0. So those are encoded with 8 bits per channel, or 8 bits for red, for green, for blue. Opacity is just in the range 0, 1, and it's continuous. And that gives you about, you see, 17 billion colors, which is pretty good because it matches more or less what we're able to see. So you can encode it in 2 ways, either with the decimal for the red, green, and blue, and then a real number for the opacity that is between 0 and 1, where 0 means that it's completely transparent. So you will not see the element that you put in the page if you set it to 0. And 1 is completely opaque, meaning that you will see the exact color that you would get if you omit the opacity. So by default, when you set opacity to null or you don't use it, then not to null. Sorry, if you says have it undefined or you don't use it, then you end up with opaque. So for opacity, the default is probably 1. So yeah, so here you see the example of how the decimal real settings are used, right? Where you put in parentheses the RGB values with each one of the red, green, and blue with a number between 0 and 255. You can also use, and don't ask me why, but people do this quite often, and the hexadecimal notation. So in there you go from you have 16 values that go from 00 to FF, meaning 15. So you need to do a little bit of math, but it's kind of practical to, if you want some red, then you put FF on the red on the first couple, and then you're good to go. Where do I have this? It's down here, right? So this I know that it's red, and it's red, green, blue. So usually at that level, that's how everybody uses it. If you see here, if you start doing conversion between the RGBA and the hexadecimal, then you need to do a little bit of math. That's easy, and I think that D3 has something to help you out there if you really need to do that. But yeah, that's about it. I put the description of how you do the conversion there in case you're not familiar with that. It's good to know. So how do you use a model to describe how colors can be mixed together? So you do this with a color model. And there are essentially 2 kinds. There is the additive color model and the subtractive color model. The one that we're mostly interested in is the additive one, because there we're mixing color similar to what happens with a projector and or a computer screen. The subtractive model is used for printouts. So if you print things on paper, then that helps you understand what happens when you mix colors and how you see them on paper. The difference being that here you're actually adding colors, hence the name additive. And here what you get is the color that is reflected, so you're kind of subtracting the rest of the colors. And that's why it's a subtractive model. What you see is the reflection of the color, and the other wavelengths are removed. So in this color model, so we're going to concentrate on the additive one here. You have what are called the primary, secondary, and complementary colors. So the primaries are very simple. Is just the three colors that you use in your to define your axis for your color space. And in this case, it's RGB. So when you mix the red, green, and blue, then you end up with white. And the particularity of the primaries is that you cannot build them from other colors that are not primaries. Yeah. The secondary colors are colors that are mixed from exactly two primaries. And you have three of them that correspond to the primaries. So you can see here on the picture. So the secondary for the green is purple, yellow, and cyan that is here, right? So yeah, and the operations here are the first one. So if we mix red and blue, then we end up here with magenta, what you see in this line, and so on. Okay, so it's all fairly simple. And the complementaries are pairs that combine cancel out, which means that you end up with white. So typically, if you take a primary and the secondary, then you end up with white. So if I get green and magenta, I end up with white. And that is this line here. Yeah. So not very complicated. So people show it either this way, or this is kind of with intermediate values where you can see the orange. This is the green, and so on. Obviously, it's a continuum, right? So that's why you usually stop at the primaries and secondary, because after it gets a little bit complicated. Okay, so which ways can you display additive? Use the additive color model to create displays. So here you have exactly four things that you can do. So the projector is one. So it's called addition of illumination, because you have lights that are projected with different colors, and they get blended on the screen according to the color model, right? You have the partitive mixing. So that's what happens with your computer screens, where you have small elements that emit a given color, and they're small enough so that when you look at them from far away, the colors blend. The closer the closely spaced colors are going to blend together, and that's what you have with your LCD screen. The OLED, that is this micro displays, they flip the colors, and that's called time mixing. And then obviously you can have a different color in each one of the eyes, and then you use the stereo vision to mix the color with binocular vision, right? And this is, you might have seen I went to the movie theater where you have the red and green lens to see in 3D. So that's a little bit what is going on. On the screen, you have the opposite. So each eye is getting one image that is slightly shifted, and then you get the impression of the display. And it's happening because your brain is able to filter that out through the lenses. So usually the colors, you try to model them in a space that is useful for the application. So the cube is okay to understand a little bit the colors and the color operation, and it's a Cartesian axis with red, green, and blue. And you're probably familiar with the cube model, because you Mac and Windows, they all have those sliders for different colors, and what they allow you is to move in this view, essentially, right? And that's okay. But people who do graphics, they tend to prefer the hue saturation value because it's easier to use and it works similar to how the brain is working. You remember that we saw that it was hue saturation and brightness. So this is more natural because you're closer to the output. And so you pick the color with the hue, and then you can adjust the saturation, the brightness accordingly. The last piece here is we're moving with the dark background, and so this is kind of complementary information. So you hear about what people call a color space, and you've probably seen this picture somewhere. So this is the sRGB color space from Microsoft 96. And so what it is basically information that tells you how a display is able to produce colors. So what colors a display can produce with some high fidelity. And that's obviously applications with computer screens, because you want all computer screens to show you the same red, right? And the space, you can basically plot it in 2 axes. That's what people do. The chromaticity, that is the hue saturation, because we are time seeing it 2D, right? And then the luminance here, that is a 1. And if you do that, then you end up with this type of plots, where here you have the temperature that is associated with the color, and here you see the sRGB space that is rendered by a given device. Now, these are the devices are calibrated so that you make sure that the color temperature is the same, and so people can see the same color. And this is done basically with pretty much the same way that Helmholtz and Maxwell is not young did the experiment with the trichromatic theory to try to understand if people are seeing colors in the same way. And the way they did this is that I was discussing earlier, you are the observer, and they show you a light here, this magenta color, and I give you knobs to adjust the intensity of the red, green, and blue light until you match this color. Where you are able to see in one eye the magenta color, and then in the other eye the mix, right? And it turns out that people pretty much go with the same knobs. So that allows you to calibrate the monitors. That's a little bit the idea behind it. Yeah, it's important to know that it used to be a problem with the CRT monitors, but now with the LCDs, you can pretty much discount that. Yeah, there is no reproduction of color problem anymore. Okay, so we'll go with color design, and yeah, so maybe I'll wait here because it's 2:58. So we'll do a little break of 10 minutes, and then we'll come back to this with the color design. Okay. Boys. Somebody has a question for, I think it's the exercise 0 or 1 for A6. And I'm asking for a deep copy with slice on an array of objects, which does work. It works if they're numbers, but if they're objects, you get a new array, but to do a deep copy, you need to copy also the object, duplicate the object into new objects, which if you do the slides, probably doesn't do it. So yeah, you can put there that with just slice is not possible. So you would need to either turn it into a string and then parse it, and which would recreate a new array with new objects inside. Or you can use some of the libraries that are out there. One is Lodash that has a deep. I think it's Lodash usually require it and put it with underscore. And I think they have a deep. And here you pass your object and return the copy. Yeah, so if you have other things, maybe we can discuss that after we finish here, because we don't have, we're going to finish early, I think, today. Okay, so with all these things about color in mind, now we're going to try to look at how we use the colors for graphics. And you have essentially three things that you can do. One is that you use it for labeling. So if you have bars, you can set colors on the bars. So you're naming the bar based on the color. You can either highlight one instance or multiple. So you can group things together, as seen here in the last example. And these are legitimate use because here this is pre-attentive. So if you use to highlight this one, then you can bet that people are going to see it first, because it's the color here is different from anything else that is around. So we're going to see it very quickly. The same way, we're going to see that there is a group there of maybe 3 or more very quickly. Not exactly, so it's unclear if you can see that it's exactly a group of 3. In this particular case, probably. But yeah, if you have many more bars and or dots, then you can only get an approximate count. Doing this, you're doubling the encoding, right? Because the bars here are labeled already by the categories, and so you're adding this other color there to basically say the same thing, which is not it doesn't make it as a minimalistic visualization, right? So you're using ink to do twice the same thing, and then what you're doing is that you're asking people to interpret that. So they're going to wonder, why do I have the labels at the same time the colors? Usually it doesn't make sense unless you have multiple graphs and you want people to track the categories across the graphs based on the color. Yeah. But usually the idea is that the less you use color, you use it sparingly, it's the best. So the second thing that you can do with color is measure, or you're trying to do things so that they look the same as what people are used to, so they understand it better. And in that case, you're really adding a color, doing a mapping between a color and a value in your data. So it can be a continuous value, or it can be a category. So here is probably a continuous variable that is associated with the color in the color-based map here. Here we're color coding this image so that we see the bodies of water, and then probably land that is not constructed is happening in green. So we have land that is built is appearing in yellow. So we have these three categories that we associate with the color. And we're using the blue and the green because we're trying to imitate what people know. So they don't need to reinvent, right? Because if we would put the water in green, then you need to make people think about changing the association that is natural already in their mind to something else for no reason, right? So you're making the user work more, which we always try to avoid. The last one is, we'll see that explain more today, but here we're doing also the same. We are associating a grid value to a continuous color scale. These things are called color scales, right? Because what they are, the same way that we've seen the scales and the axes. So this is a color scale and a color axis that is represented here, that allows you to read the color based on the value. Yeah. So in D3, we're going to see how to do those color scales, obviously. And also the types of color scales that we have, depending on if you are using a continuous color scale or a discrete one. The last example is the last thing that you can do with color is to enliven, which means here to be explicit. If you don't know the word, it means to make things more interesting, more attractive, or just for make it more pretty. And so you just add some decoration around, right? With all that. So yeah, when you hear the decorate and enliven, you should think about the minimalistic visualization and be careful with using color outside of the graphs, because what you're doing is obviously detracting people from focusing on what is it that you want to show them as information, right? So when it comes to images, people differentiate between different named colors. So we have a lot of imagery today because you get satellites that are flying all over the place, and then people are also taking pictures that you can do virtual reality with. You can augment the picture, and in doing that you can use colors, right? So traditionally you have what is used true color, that is the color that you would see if you would be where the sensor is at and you look at the scene. So here, for instance, we see the clouds, we expect them to be white, they're white. It looks like a river, and there we see some woods. So this is typically what people call true color. The opposite of the true color are these things that are called false color and pseudo color. That really are about having a different mapping between the image and the colors that are used to color parts of the image. So those have been created mostly because the satellite sensors, they don't do RGB. Here you see, I think this one, it's energy that is near infrared, and then red and green. And so you need to map the near infrared to something which usually people map it to the red. And then you end up with having the golf courses here that they got that are shown in red, right? So these are actually grass and shown in red in this picture because of the way the sensor works in terms of bandwidth. And so those are false color in opposition to true colors. The difference between the false color and the pseudo color is that you are looking at a grayscale image. So typically an infrared image. And so you encode the intensity here between hot and cold, right? So here we see the animals that are cold bodies in a cold landscape where the dark, the zero means that it's is the coldest that you have in the frame there. And you see that it's 16, 17 degrees Celsius, which is not that bad for cold, especially if this is at night. So the false color techniques, this is a problem. There are essentially two. One is the by extension. Here you need to see that it is not directly these have been created for the satellite images, but these are more charts that people have created for information visualization. And so this technique really are mapped by extension to this category of false color. So one is the color-place map, where you associate, and this we're going to see it in detail next week, you associate one area with a value by encoding with a color scale, a continuous color scale. The other technique is to do what is called density slicing. So the example that we saw a moment ago is a good example of density slicing. That is here, where you basically encode a range of gray values or colors, multispectral, into one particular encoding for a color, and you do this for multiple ranges, so you get this areas that get naturally colored in this way. So again, all the maps where we're going to look into that next week. So then next week, I think that's the kind of the most complicated that we're going to see, and after that we're pretty much done with the free, which I guess people will be up to learn. But yeah, the maps are really the most complicated, and I would say the most useful. So next week, if there is a need, we'll spend a little bit more time on that. So what are some good design guidelines in using color and different colors in the same page? So the take-home lesson is just to be careful when you do colors that are mixed together here in the page, and where one contrasts with the other. So that's called color contrast. And there, the thing that you want to be careful with is the simultaneous contrast that we saw earlier. So the blue text here on the black box appears completely unreadable, and that's because we have the fewer blue sensors. So that's the trichromatic theory that tells us that. And so you want to avoid to put blue color on a dark background because it creates a problem with readability. Now this is again with text, but if you have blue dots because you do a scatter plot on a black background because you want to have a night mode for your dashboard, then you see that the spatial resolution of the dots is going to be compromised. The red and green, you see that they're equally, or maybe the green is a little bit better. And that's because we have about the same number of red and green cones. So that's a better choice. The ultimate best choice is to go achromatic. And the reason is that when you do that, you're using all the sensors that you have in the eyes at once. Because achromatic, you remember, is the sum of the green plus the red plus the blue. And so if you have either white text on a dark background or light text on a light text on a dark background, or light background with a dark text, then you are basically using all the receptors, and it's why this is the not surprisingly the best that you can do, right? Yeah. So when you with the so this is. So this you can only do it obviously mostly for text, and or if you really do a minimalistic chart where you're just keeping the encoding, you don't make them redundant with adding color, where you can use another technique. That will carry on with this. But as soon as you want to use different colors, then the question is which colors should you use? So the trichromatic theory tells you that you can use either the primaries or the secondary colors that will kind of work, but that you need to be careful with people who are red-green blind. And the component channel theory tells you also the same for the red and green, but also that you can do yellow and blue or blue and yellow, and that will work very well, right? And that's why you see some of the maps, they use blue and yellow. That is because there are two channels that are opponent, and that the brain is very good at differentiating, right? So that's a kind of natural choice. And then you've seen it in some electoral maps that go and use these colors. So yeah, that's usually a much better choice than to do the red and green, obviously. That's the shortcoming that we discussed. So the complementary colors here that I've discussed with that a little bit. So yeah, if you do the complementary colors, then it's also usually a good choice. So we're going to see in the lab how do you maximize the color contrast depending on the application. So usually the norm is to do a AA. So we're going to see what that means. But in some application, you want to have even higher color contrast. And the browser has some tools that can help you with that. That you can also obviously use on charts. So sharpening is another technique that you can use. And basically what it boils down to is that we don't perceive the differences between lighter shades when compared with each other and darker ones. So it turns out that we're better with darker than with lighter. And here you can see it in this picture here, where you see that here we can very clearly see the difference between these two colors, but the difference between the lighter color is much harder to see, right? And so using this effect of sharpening tells you that you're better off using darker colors. And you can play with the background, because the background does a little bit of changes a little bit the way we perceive, because if you change the background, it's interfering with the colors that you're reading for the different colors here in the keys. And usually, as you can see, it kind of does a better job here, closer to the light colors than it did before. Okay. So here, I mean, with the projector, it's hard to see, but so what that tells you is basically if you have a lighter background, then it's okay to start using lighter colors because people will be able to differentiate them. Otherwise, you know, the ways the dark colors are good to use. So this is a discrete scale here, and here you see pretty much in the same way, but with a continuous gradient of the colors here. So it's the same effect. So when you need to create any graphic, you need to come up with a set of colors that are going to be good to use. And what you don't want to do is pick those by hand, just because you like the color. The reason is, as we've seen, that the colors interact with each other. And if you want to have a scale, a color scale, that can be of different types, and we're going to see what the types are, you need to pick the individual colors in the scale. So here, these are discrete scales, but you can make them continuous if you want. So you need to go and pick this particular colors here. And what you want is usually maximize the difference between any two colors so that you can resolve them, right? So if you do this by hand, just saying, oh, I'm going to interpolate between color A and color B in a linear fashion, it is not going to work because that's not how the brain works. Because the brain does this complicated thing of accounting for differences in colors and so on. And so the mapping is non-linear. So folks have spent quite some time developing color scales that are good in that they maximize the quality of the scales in terms of how it is perceived. And so that's usually what you want to do, even if it's to go and pick 3 colors. Okay? So a good example here is, and we're going to see in the lab how to use it. And maybe if we have a little bit more time, I can get started with that. Is Color Brewer. So this is a website that is online. There is another tool there that I mentioned, is Color Oracle, and we're going to also play with that a little bit. And what they give you is the ability to pick a color. So if we look at this, we see 3 different patterns here, right? There is all of these scales, they seem to share the same pattern. Then we have this group here, and then we have the last group, right? So here, this is useful for values that are either increasing or decreasing, and you want to have some type of mapping between your data and the values, right? And so this is one type of scale. Here you see that you have 2 scales in one, right? With 2 opposite. So this is typically where you need to do opposing. You have opposing measurements: hot, cold, polluted, not polluted. Yeah. So it's kind of a dichotomous scale here, where we're divergent scale, where we have some value in the middle that is maybe the normal, and then you can move up and down. And this one is kind of the old one that is the patchwork thing. Any idea what this is useful for? Why would you choose this one here? This is actually the most used. Idea? Categorical data, yeah. So exactly. So here, what we want from these scales is that every color is unique, so we can't confuse one with the other, right? And you see that the larger one here, they're very good, right? But then we start having some redundancy because obviously we have only a few primary color and a few secondary color to work with. So eventually there is some duplication that happens. So here we have the light green and the dark green. Yeah. Still, it's very clear that they're different, but you might start thinking that the green is one subcategory and the blue is another subcategory, which usually leads to confusion. And the other thing that we see is that as soon as you start adding this number of categories here, right, it's complicated to go and remember which color is for what. So you'll end up moving between the legend and the graphic all the time, trying to understand what is what, right? So the more you have, the more complicated it is, right? So you want to be very careful with the color encoding because it can get just overwhelming because all these colors are also very attractive to the eye, and so it's just even more confusing. And so the number really has to do with our ability to remember things in the short term. So usually you don't want to go above 5 to 7. We're going to repeat that at some point. Yeah. Now these are just examples of two continuous scales, right? So this is the hot and cold, and this is one similar to this one, but is discrete on top. So we're going to see those more in detail. So here in this slide, where we can actually give them names and understand a little bit the characteristics, but that's basically what I explained now. So the first one, the colors are following each other closely. And here, typically, you have a linear mapping between either a low or high value, depending on how you read your scale, and the other extreme. Okay. And that's called a sequential scale because each key here follows the previous one, and that's an order, right? That is the order of the data. The diverging one, I've explained it. So here in this particular case, they have this white rectangle in the middle. So that's called the critical value. Sometimes you have such a thing, there is a 0 and you want to show it in your data. Sometimes you don't have that. In that case, you can omit it, right? So your scale can start from the two keys that are out. And so that's basically two sequential scales put together, right, for things that are opposing. And then the qualitative scale, that is for categorical scale, you can call it both ways. So this is for things that you can make. And we've discussed why everything needs to be as different from each key as possible. So some closing recommendation. I think I have a few slides for this, and these are useful, I guess, for the projects. So in general, when you put together large displays. So for some of the charts, people tend to use some specific color scales. And so if you try to invent this, you're not making them a favor because they need to re-understand the color scale and reinterpret the images. So if you look at the pollution maps, traffic maps and so on, people tend to use specific colors, right? And so you want to first go and make sure that you are not reinventing the wheel. Some of these colors might have some color scales might have some problems. If you look at the air quality index map, so some people put a lot of keys in there, and to me it seems a little bit confusing. But I guess if you're an expert in that domain and that's what you do all day, that is what you want to do. So you want to make sure that you know about that. Some places tend to associate specific meaning to certain colors, and so as you, depending on what your data is about, obviously you want to be sensitive to that and make sure that you don't trample over conventions in your graphic, because again that distracts the user. When you put together any dashboard, you end up having to decide for some type of color scheme that you're going to use throughout all your pages, and also for the graphics. So the graphics is really data dependent, right? So, because sometimes you might need to have certain colors for a given graphic. The graphic are independent. You don't need to relate data points with say color across the page. Then you might not need to think about that, but you still need to think about it in terms of consistency in the page, because if things, the layout, etc., looks completely different, then people need to adapt to it each time they change from page to page, and that just makes things more confusing. And so usually what you do is that you go and get a color palette. You can go online there. There are websites that specialize on that, and they give you a few colors that you can use as your main theme. Okay. So these is what I ended up doing. I went online and I color palette, and there are tons of websites that give you these little thumbnails there with a few colors that you can start using to build something consistent. If you do that, then you can take care of your UI part, and then for the part that has to do with the graphics, you can do the same, but there it's really consistency. And you want to keep in mind, this is the Google thing for the Google Analytics, and here it's mostly purely visual. They don't try to relate one chart with the other. So you see that here this is the up, so you've got a sequential scale here that is used. But here, this is a categorical scale because we're coloring different countries with a different value. And these scales might not be the same, right? But they're trying to use the same color so that the whole thing looks homogeneous, and that's fine in that way. The other thing that you can do is relate the data. So if you're having the same countries in a map and on a bar chart, then you can use the color for that. With the caveat that obviously you're in one of the charts, that is the bar chart, you're encoding twice the same thing, which is a little bit confusing. But if it's next to the map, then it might be useful. The color brewer and all of these tools that allow you to pick a color scale, they usually have a good option to provide you with for colors that are colorblind safe, meaning that you don't need to think about if you use those color, if people are going to actually see your data, because the colors are such that they're set up so that any colorblind person would be able to access it. Yeah, this would see the color contrast with the different standards. We would see it in the lab. I think it's easier to see it here. If we have time, I can show you a little bit of color brewer while we're at that. So the reading for this week, that is the, not remember the chapter, but it's from where, is very good with recommendations. So this is one that is coming from there. And it's basically obvious, is that don't use too many colors, especially what people call accent colors, that are those that come the most at you, because you're creating visual confusion, and that's not going to help out people resolve their visual queries. So you remember that we say that one of the things that you want to do when you put a chart is think about what information you want to bring forward, and you want to reserve the use of colors, in particular accent colors, to make those visual queries that are related to the important information stand out. And so you make a good use of the color, and you don't interfere with the rest of the information that might be secondary. Usually also, and this is not touching into the dark mode displays, but if you're with light backgrounds, then usually the good rule is to avoid to color large area with dark colors, because then what happens is that visually you're not able to see the grouping and the connection as easily than when you reserve you use light colors. The lighter, the larger the area, so that the smaller the area, the more accent colors, and yeah, so that works here in the example, and it also obviously works if you're thinking of these as a scatter plot, right? Because your data points there would come out better. Yeah, but yeah. Okay, colors in D3. So sometimes you need to manipulate these color scales dynamically. So D3 has some utilities for that. So if you want to go from one color space to another one, so here we go from we can go in this color space that is hue, saturation, and luminosity, HSL. And we want to encode this color that is a named color, still blue. You can just set it as a color in an HTML element to see what it does. So if you want to convert it and see what it looks like in HSL, because you're doing something where that color scheme is necessary, then you can do it in this way. Sometimes you want to get a key that is a little bit darker or lighter if you want to highlight something, but still using the same color. So there is a darker and brighter that you can also use. And then you have utilities for generating color scale. And these are includes the color brewer scales and other scales. So you can go in color brewer and say, okay, I would like to get this particular color scale. And then in D3, you can configure it. There is a page where they're listed. You go look at the same with the same colors. And then it's going to give you here an array of colors that are the color scale colors that you can just use. Yeah, so some not all, everything is loaded by default. So you see that HSV, for instance, is another library, and that's because most of the time you don't use it. But if you need it, they're in a separate library that D3 provides. So the color scales, they're used in pretty much the same way that we've seen the scales, the linear scale, the log scale, etc. And you remember that there were a few of these other scales that we said we're going to see this later, which is the quantile, etc. So you can use all of these for color pretty much in the same way we did with the linear scales and categorical scales that we've been using. So here, obviously, the sequential scale will give you what you expect, right? So we're going to map. You need to map a key in a color to a value. Then that is going to be useful for that. And you have obviously these combinations of continuous data and or discrete domain and range that you can play from. So the table is not that useful, but know that for each color scale, basically you have some functionality in D3 that allows you to generate that. And the last bit here, and I think, oh, I'm past the time. Okay, I thought I had plenty of time, but no. This is just the last slide. We're going to see this in the lab. So this is the library that D3 provides to do things that are much more complicated than what we've done until now. That don't just search the data. So the generator here are going to do the line chart. You need to change your data to the line segments. And then you can do the data join with that. Same thing with the area, pie chart, and so on. But you have some of these that really touch at the layout of the whole graphic, and they allow you to do complicated things with boilerplate that is already there. So we're going to see how to do the chord diagram and the Sankey diagram and so on as examples. But there are much more than that you can, once you know how to do a few, then you can just go and use from the D3 library. Okay. Thank you.